Welcome to lecture 17, which I'm going to talk about wave kinematics, which means I'll be talking about the basic sort of quantities that we use to describe a particular wave. And we'll be focusing entirely on sinusoidal waves, so waves that look like a sine or cosine function. And as promised in the previous lecture, I'm going to eventually explain why those are so important, the sinusoidal waves, why it is so special, and how are they sort of the foundation of any other wave shape that you can think of. But I'm going to postpone that. Right now we're just talking about sinusoidal waves, how to describe them. So here I've got a snapshot graph, right? Remember, that means you go to the camera, you take a picture of an ocean wave, and it looks like this. Now, I'm not saying that the scale of the displacement is the same as the position, right? Like one meter along here might not be the same as 1 meter along here. This might be, 2 centimeters, and this might be 1 meter, 2 meter, 3 meters. Could, of course, be that the displacement isn't a length at all, but a pressure change, if this were to represent a sound wave, for example, right? So, but it's easiest to think of it as a physical, like mechanical wave, say the surface of the ocean. Easy to visualize that way, but you shouldn't assume that every time you see a graph like that it is literally a physical displacement by a certain distance. It could be the value of the electric field if this were an electromagnetic wave. Alright. So how do I describe this? So the first thing is the amplitude. The amplitude is pretty much what you know it to be from having studied oscillations. If you want to make it as precise, I can imagine if this were an ocean wave, I put my rubber duck somewhere, it's going to go up and down. In fact, it's going to go up and down in the manner of simple harmonic motion if it's a sine wave that's sort of passing underneath it. And the amplitude is the how high does it get, or equally how low does it get down, right? That's also the amplitude. The sine function is the same above and below. It is not the distance from the very top to the very bottom, right? It's half of that. The second thing I can talk about is the wavelength, and that is literally what is the distance from one peak to the next, or from one trough to the next, or from this point here halfway going up to the next time this point happens, right? So over here. That's what we mean by the wavelength. Now sometimes you want to sort of express not directly the distance, but you want to say, well, how many waves do I have within, say, 1 meter? Like, how many waves do I have per meter, right? So the analogy is you've got a frequency and you've got a period, right? A period tells you how long does it take to go up and down once. And then the frequency is, well, how many times a second do I go up and down? And the angular frequency is how many times a second do I go up and down times 2 pi, essentially saying how many radians of cycle am I moving along. So the same thing happens here, and so one quantity is a little bit funny when you first meet it. It's called the wave number, and we give it the symbol k, which is annoying because it's the same letter we use for the spring constant. Well, there are no springs here. From the context, it's usually clear which it is, right? Like most letters of the Latin and Greek alphabet, it's overused in physics. The wave number k, and now you might think it's 1 over lambda, right? It would be like the number of waves per meter. If the wavelength is 20 centimeters, 0.2 meters, then you'd have 5 waves per meter, or 1 over 0.2. If the wavelength is 2 meters, you'd have half a wavelength per meter. But then we multiply this by 2 pi, so this is essentially the analogous thing to the angular frequency omega, but across space, right? I freeze time and I look, well, how many sort of radians of phase do I have per meter? So the wave number is. But conceptually, it expresses the density of waves. more often than not, we're going to talk about the wavelength, which is a lot easier to visualize. Now, those are not all the quantities. Of course, the wave is traveling along, right? And it's traveling along with a certain speed, v. Right, so this is my speed. I can't draw this, but if v were, I don't know, let's say half a meter, then after meter per second, then I would, if I took another snapshot 1 second later, I would have shifted the whole graph 1/2 meter to the right. The speed was half a meter per second, right? Again, you can visualize this, stand at the beach, the waves are coming towards you, you can track, say, the top of this wave, see how it's moving, tracking the pattern, that'll give you the speed. Another thing you can measure is the period, right? The period is essentially what you think it is. Imagine you put your rubber duck here, and it's ocean waves, and the rubber duck moves up and down, and it's going to do simple harmonic motion. Period is the time it takes for one full cycle at a given point. Period t is the time for one full wave cycle to pass a given point. So again, try to imagine you place your duck here, and as this wave moves to the right, as the shape moves to the right, the duck that's riding the surface is going to move down. When this point here is moved over here, then this part is going to move past this one's going to go back up. When this point when this point is moved all the way over here, right, the duck is highest, goes back down, and then it's going to be at that same spot again, but one wavelength on. And that's the period. Now you can imagine what we're going to define next. You can define the frequency f, and that's of course 1/t, right? The period is 2 seconds. That means I have half a wave per second, 1/2. The period is 0.1 second, probably not ocean wave, some other wave, 0.1 second. Well, I'm going to get 1/0.1, that's 10 oscillations per second. Then of course I can define the angular frequency, omega, which, as you might guess, is 2 pi times f. So those quantities are exactly like for the ones for simple harmonic motion, and you get that by placing your rubber duck here on the ocean wave, and it goes up and down. And that displacement has a period, it has a frequency, it has an angular frequency, and those are exactly those quantities. Okay, so how are they related? Is there some relationship? So there is, and the relationship is with the speed. So here's what I want you to imagine. Imagine you're standing, you walk out into the water. Again, we imagine ocean waves here, and there's the tip of a wave, like the crest passes your hip, right now. Okay, then you wait, and a little time later, the next wave crest passes your hip, right? So the time it took for that was one period, by definition, right? From one crest until the next crest reaches that point. But in that one period, what distance has the wave traveled? It's traveled, well, exactly one wavelength, right? So the upshot is that the speed of a wave is the wavelength divided by the period, right? Again, because the time for this point to reach this point here, you're standing right here, you're not moving. The time for this point to get to here is exactly one period, because right now at the top, you're waiting for the next top, the next crest. The distance this starts off being away is one wavelength by definition. So the speed is one wavelength per period, right? So lambda over t, and of course I can rewrite that as lambda times the frequency. And this relationship is very important. Right, so we're gonna need this one a lot. Okay, now let's look a bit more closely at how we can describe the shape of the wave as an actual function. So here I've drawn a simple sine function. Right, that's representing my, let's stick with ocean waves. Could be anything else. So my guess would be the displacement, let's call it displacement big D, right? My guess might be, I might run it, okay, D, what is it, what might I write down? Excuse me. D of x is sine of the position x, right? Of course, that's not going to work. Has the wrong amplitude and the wrong wavelength. How do I know this? Well, what is the amplitude of this? Wrong amplitude. The amplitude here would be 1, because sine goes from -1 to 1. Has the wrong wavelength because, well, when is one full cycle complete? When x reaches 2 pi, right? So it started 0, then I got pi over 2, pi, 3 pi over 2, 2 pi. Now one wavelength is complete. That's my wavelength. Okay, those are both wrong, right? Unless by chance my wave has an amplitude of 1 in whatever units and a wavelength of 2 pi in whatever units, okay, then this is my function. But in general, that's not true. So how do I fix that? Well, so this is wrong, right? So let me try my next attempt. I want to fix the amplitude. I'm going to say A sine of x. So now A times the sine function means it indeed does go between -a and +a, right? So now it's just the wrong wavelength. So how do I fix that? Well, here's my thinking, right? The sine function reaches one full cycle when the thing inside the sine function is 2 pi. Right? Let me write this down. Sine of something, let me call this something theta, because it's sort of like an angle, right? Equals 0, or let me just say this. Sine theta has gone through one full cycle once theta has reached 2 pi. I assume it starts at 0, and I move along, it increases, but I want this thing inside the sine function to reach 2 pi. So how do I make that happen? How do I make it that this here is lambda? Well, I want the thing inside the sine function to be equal to 2 pi when x equals lambda. So theta is my argument of the sine function, also known as my phase. Theta equals 2 pi when x equals lambda, right? So x starts at 0, it keeps getting bigger, and once I reach the value lambda, maybe 2 meters. 2 meters of wavelength. Once x has gone from 0 to 2 meters, I want the thing inside the sine function to have gone from 0 to 2 pi. And you can check that it happens if I let d of x be equal to a sine, well, 2 pi x over lambda, right? Because now, if x is 0, the whole thing is 0. then x grows, and when x is equal to lambda, well, this fraction is just 1, so I'm indeed at sine of 2 pi, 1 full cycle is complete. If x were half lambda, well, then I get 2 pi times a half, which is just pi. It would take me to here, like sine of pi. It's this point on the sine pattern. So that works again, right? Half a wavelength. So this gives me the right expression. Am I done? Not quite, because this, right, is a graph at one given time. Maybe this is at t equals 0. So this function that I've derived, I've sort of constructed, that works, but only at a given time. But how about other times? Right, how about other times t? Well, so here's the upshot. I want to move this wave to the right. Right, it moves to the right with some speed v. Right, it has speed v. So that means at time t, at time 2 seconds, it will have moved 2 times the value of the speed over. Right? Change in position is speed times time. Right? So at, let me write this down, the answer is at time t, the wave has moved to the right by a distance t times v, velocity times time. Okay, how do I move a function to the right by a given distance? So hopefully you know how to shift a function left or right. But here's the answer. So suppose I want to take my function and I want to shift it to the right by some distance s. How do I do that? So what I do is I take the x, every occurrence of x in the function, and I replace it by x minus s. Here's some examples. Imagine my function is the blue one, y equals 2x. This is my f of x. It's 2x. I want to shift it to the right by 3 units. So what do? I go y equals 2, and then I replace x by x minus 3. Now you can check that, right? How might you check it? Well, you can think of it this way. Imagine I want to figure out what happens at the value x equals 4. It's right here. Well, I plug in x equals 4, but it's almost like the minus 3 makes the function look up the value at the point x equals 3, look up the y value at the point x equals 3 after subtracting 3, after going 3 steps to the left. Okay, here we are. Alright, so it says, wait, 1, 2, 3 to the left. That's what a minus 3 does. Okay, let's look up this value here, and indeed that's the value I get. And it works with any function. Right? So imagine my function is y equals x squared. Well, if I want to shift it to the right, I'm going to say it's y is x minus, well, I'm going to shift it by 7 units, x minus 7 squared. Notice it's not x squared minus 7. That would shift it up or down. The x itself, the occurrence of the argument, that is what gets shifted. If I've got x appearing 3 times, x log x plus x, well, just replace every x by x minus 7. You're going to shift the whole function to the right by 7. Right, so no matter how complicated the function is, this works. I'm going to shift it to the left. It's sort of like shifting to the right by a negative number, or just I add 5. How does this make sense? Well, let's suppose I want to figure out what happens at the value x equals minus 7 right here. And this is my function. Well, it's sort of like it says, okay, x minus 7, but actually I'm going to look up the value of the function x squared, but 5 units over because I'm adding 5 first thing. For 5, I'm looking here. Alright, that's the value. I'm looking at the original function. Maybe that helps you remember how to do this sort of thing, right? You visualize the function, visualize what it means to if y equals x squared. It means for any x value, you sort of look up what the y value is on this graph. Well, changing your x before you do anything else means you're looking it up, shifted to the right or to the left. Maybe that helps. So let's apply this to our function. Here's what that looks like applied to our function. So the function was this, right? The displacement as a function of position was this, at time t equals 0. Now I want to shift it to the right by s. I indicated this by having this little subscript to the right s. It's not any kind of official way of writing this. I just made this up, but I think it's clear what that means. So I take this function, I take x that appears here, I replace it by x minus s. Now what is s? S, the distance by which I want to shift my function, depends on time. So for us, s is, we said, v times t. Right? V times t. Because that is the distance by which the wave will have moved after time t, times time that has passed times the wave speed. It's basic kinematics. So let's plug that in. So what am I going to get? I'm going to get the d, and now I can write it essentially as x t, right? It's a function of position and time. It's going to be a sine of 2 pi, and then I've got x minus vt over lambda. Now, you could leave it like that. We're going to do a little bit of simplification here, right? I'm going to do a simplification as follows. I will write this as a sine. Let me split those up first. 2 pi x over lambda minus 2 pi vt over lambda. Okay, we can simplify this further because v over lambda, what is that? That is, of course, the frequency, right? We had this right down here. The speed is lambda times f. Well, what I have here is v over lambda, so I can write this as f. So I can write this as a sine, pull the 2 pi out, 2 pi over lambda x minus 2 pi f times t. Now we could again leave it like this, but we can just simplify it a tiny bit further. 2 pi over lambda, what's that? Well, we had this earlier. This is this thing. This is the wave number k that tells us how many radians of phase do we get per meter of distance. Or in other words, how many full waves do we get per meter times 2 pi. And then 2 pi f is, of course, omega. Let's note that down. I'm going to get my final answer, that d x t, the displacement as a function of position and time, because the rubber duck on the ocean, how high up it is depends on where do I put it and at what instant in time do I look, going up and down. And it's a sine kx minus omega t. 2 pi f is omega, 2 pi over lambda is the wave number k. So this is the mathematical description of a moving wave, moving along a line. We can worry about how to describe waves spreading, say, in 2 dimensions in the future, But right now, make sure you understand how to derive this and what it is, what it gives us, right? A moving sine wave. To finish off, then, let's look at one example. Say the question statement is the following: a particular ocean wave is described by the function dx of t is 0.2 meters, presumably, times sine of 3x minus 2t. So I read off, comparing it with this, the amplitude is 0.2, k, the wave number is 3, and omega is 2. How do I find the speed from this? Well, let's figure that out. So we read off A is 0.2, and I'm going to assume it's standard units. K is equal to 3. The units technically is per meter, or radians per meter. And then finally, I read off that omega is 2 radians per second. So I want to find the speed. Well, what do I know about the speed? I know v, speed, is lambda times f. But I don't have lambda and I don't have f, but I have k and omega. Well, I know that k is 2 pi over lambda. So that means lambda is 2 pi over k. You can write it like this. Times f. Well, I don't know f, I know omega. But what I do know is that f is, or maybe we should write like this, omega is 2 pi f, right? And so, hence f is omega over 2 pi. Now that's kind of nice, because it means that 2 pi's cancel out, and I just derived another expression for my speed, angular frequency over the wave number. So in my case, it's going to be 2 radians per second divided by 3 radians per meter, which comes to 2/3 meter per second. Or if I want to do it, if I don't like fractions, 0.67 approximately meters per second. So that answers part A. What is the speed of this wave? Now, let's figure out part B. This one here. What's the maximum speed of a seagull as it bobs up and down? We're going to ignore the fact that ocean waves have a little bit of a sideways component too. The seagull just sits in the wave, going up and down, up and down. What's the maximum speed the seagull has during this motion? Now, that speed is, of course, not the speed of the wave, right? The speed of the wave, v, is how fast the wave travels sideways. So let's figure out what that maximum speed is. So here's what we have. We have d, x of t, let me just write it down again. It's a sine kx minus omega t. So the seagull is at a fixed position x. Right, so this makes this a constant. Maybe I can decide that the seagull is at a position 0. I take my coordinate system, I put the seagull at 0. It's the easiest, or I could just put in some other value. Let's leave it general. Seagull at x equals x seagull. Right, so this was my variable. I can plug in a value. This is a fixed number. Maybe it's 5, position 5. Right. Fixed value. wherever the seagull is. Right, e.g. x seagull equals 5 meters maybe from the shore or from wherever I've measured it, right? Doesn't matter. It's a fixed value, it's not a variable. So what do I have then? That means I have that d seagull, the position of the seagull, it's only a function of time, right? It's fixed in the same spot, is d, the surface, the displacement of the water, at the position x seagull t. It seems a bit abstract, right? But bear with me. So I get a sine kx seagull minus omega t. So this is just a constant. So it's really just a sine function with omega t and some constant added to it. The fact that the constant comes first doesn't really matter. The fact that there's a sine minus sign here doesn't really matter, because minus a sine function, like going along a sine function backwards, still a sine function. So what's the speed of the seagull? V seagull, in going up down, I'm going to write it down explicitly. The world's longest subscript, 2-line subscript. What is that? It is the rate of change of position of the seagull, right? This is the height of the seagull. Say from this is the flat water. If there were no waves, it's above it, is it below it, moving up and down. Well, that's the function that tells me the height of the seagull. So how do I get the speed with which the seagull moves up and down? I'm going to take the time derivative of the position. d seagull dt. Right, that tells me how quickly the position of the seagull changes in its up-down motion. Well, I can take a time derivative of this. It's going to be, it's a sine function, a is a constant. This is a constant, doesn't do anything. I've got to, the sine becomes a cosine, and I'm going to take out the thing multiplying the t, which is minus omega. So it's going to be minus omega a cosine kx seagull, that fixed position of the seagull, minus omega t, right? The x position is fixed, the y position or the d position goes up and down. The rate of change of that is what I've just derived. Notice the minus sign is not from the fact that sine goes to minus cosine. It doesn't, that would be a mistake. But from the fact there's a minus sign in here that multiplies the t. So this is an expression for the up-down velocity of the seagull. Now what's the max speed? V max of the seagull going up-down. Okay, even longer subscript just for the laugh of it. Is therefore going to be the maximum value of this. Well, this is just between 0 and 1, the cosine, so it has to be omega times a. We sort of could have guessed that, because we know if a sine function passes underneath you, underneath the seagull, then the seagull would undergo simple harmonic motion, right? Sine of omega t, okay, minus sign doesn't matter, it just flips the function. Constant doesn't matter, it's really just a phase factor. So we kind of knew already that the answer was going to be a times omega. Let's plug in the values. We had values, in our case omega, let's look back here, omega was given by 2 and a was 0.2. So this was 2 radian per second times 0.2 meters. Now, radian is not really a unit. This is 0.4 meters per second. Right, and that is my final answer. So fast the seagulls move as it goes up and down. Speeds up to 0.4 meters per second on its way down and on its way up, as that wave given by this function up here passes underneath it. Now what I recommend you do is that you again go to a graphing calculator that's easy to use, and just play with this function. Like, try out different values. Of course, you're going to plot it either against t or against x, unless you've got a sort of 3D graphing calculator where you can have two variables. And just to see what it looks like. See, what if you change kx? What if you change t? Make it a function of x, make it a function of t, right? You get those history graphs, the snapshot graphs. We learn math by handling it. Right? We learn math by playing with it, seeing the patterns, getting familiar with it. Abstract proofs, they're great. We need those, but they don't really make us understand how something actually works in practice. Right? So we do need both those aspects. We need the proofs. We also need just the playing around with the functions and the numbers to get familiar with them. All right, thanks for watching.